Hello everyone. So in this video we are going to talk about some advanced material in context with the cascading behavior on networks. So the first thing that we are trying to study is, till now we have seen, basically we were talking about there was an old technology B in the network. At some point in the time, some people in this network, some risk takers, they adopt the technology A, and then the cascade of technology A starts flowing in the network. We reach to a conclusion that most of the time it depends upon the quality of technology A whether it will be able to produce a complete cascade or not. So now we try to answer a different question. Is it possible that our network is somehow structured in a way that either accepts easily the arrival of a new technology in it, or does it hinder the spread of a new information? So the question that we are trying to address is, are different network structures more or less hospitable to cascades? For answering this question, we define a new value that we call cascade capacity. So cascade capacity is the largest value of the threshold for which some finite set of initial adopters can cause a complete cascade. We'll try to understand it using this example. So from now on we'll try to model our networks as infinite networks, that is as if they are having infinite number of nodes, but number of neighbors of every node will be finite. As before, initially a finite set S of nodes will have adopted a behavior A and rest of the nodes will have behavior B, and we can see that as the process repeats itself, a new node adopts A if more than Q fraction of its neighbors have adopted A. Now let's try to see how do we find cascade capacity for this particular network. So we know as the value of threshold will decrease, it will become easier for the nodes to adopt a technology. That is, if my threshold is 0.8, it will be difficult for me to adopt a technology. If my threshold is 0.2, then I only need 20% of my nodes to adopt that new technology for me to adopt it. So that's why we are trying to find a upper bound on this threshold, that starting from some nodes in the network or any nodes in the network, what is the upper bound on this value of threshold for which you will have a complete cascade in your network. So try to look at the network shown in the figure. Here all the nodes have technology B, but the two nodes which are shown in dark black colors, they have adopted the technology A. Now let us say the value of threshold to be 1/2, or precisely less than or equals to 1/2. So if the value of threshold is less than or equals to 1/2, in the next step V is going to adopt this technology, because V has only two friends and out of these one have already adopted the technology. So V is going to adopt this technology. Similarly U. Once V and U adopt A, X and W will also adopt A, and the process will go indefinitely, and overall we can see that it will be a complete cascade. Now we know that for the value of Q less than or equals to 1/2, there is a complete cascade, but we want an upper bound on the value of Q. So it can be noticed here the upper bound on the value of Q is also 1/2, because if I increase the value of Q to be above 1/2, then we can see neither V and nor U, they are going to adopt this new technology. So in this particular case, the value of your cascade capacity is 1/2. Consider this two-dimensional network. Here again it's an example of an infinite network. Similar to the previous example, all the nodes have adopted B, but the black nodes, they have adopted A initially. So can you go on and then try to find out the cascade capacity for this network? If you have solved this example correctly, you will find that the cascade capacity for this network is 3/8. Now you can see that a higher value of cascade capacity shows that the cascades can happen more easily over this network. no matter the quality of the technology. So higher the value of cascade capacity, more amenable your network is, or more vulnerable your network is to the new technology. So even if the technology is bad, it means that your network is structured in such a way that cascades are meant to happen over such a network. Now let's try to answer a more deep question. What do you think is the highest possible value of cascade capacity? And we have a lemma here that the maximum possible value of cascade capacity is 1 by 2. You can have no network in which the value of your cascade capacity can exceed 1 by 2. Let us try to prove this claim. So I show you a network here. So all these nodes inside this oval, they are the ones who have adopted the technology A, and the nodes outside this oval have adopted the technology B. Now initially you see V and W, they have adopted the technology B, but in the second figure they adopt the technology A, and hence they come inside this circle. So this is how the process moves on. Now consider this. If your whole of the network was to be infected, if there was a complete cascade, then your cascading process should go on indefinitely, because your network is also of infinite size. If we prove that your process of cascading will stop after a finite number of iterations, it means that our lemma holds. Because after a finite number of iterations, no node will shift from B to A, which shows that there are some nodes in the network which are still left to be converted from technology B to technology A. Let's try to prove it, that the process of cascading will stop after a finite time. So let us say that there are initially I number of adopters, that is, there are I number of people who adopt the technology A in the starting. We have 3 kinds of edges here. I would like to explain it with this slide. Okay, so you know that inside this oval, all the nodes, they adopt technology A, and outside are the ones who are still on technology B. So you can see that all of these edges which lie outside this oval are the BB kind of edges. They are the edges between the two people, both of which adopt the technology B. Similarly, the edges which are completely inside this oval, they are the AA edges, both of which have adopted A. And the remaining edges which cross the boundary of the oval, they are the AB edges, that is, they connect an adopter with a person who is still with the technology B. So we call these AB kind of edges as interface edges. And if we prove that as soon as a shift occurs on this network, as soon as a node shifts from B to A, size of the interface strictly reduces. It means that after a finite number of steps, your size of interface will become 0, and as soon as size of interface becomes 0, there will be no more possible shifts. So what we are left to prove is that as soon as a node shifts from B to A, the size of your interface will strictly reduce. Let us try to see how does it happen. So suppose this is a yellow node here which has some connections with the neighbors who have adopted B, and some connections with the neighbors who have adopted A, and this node is going to shift from the technology B to technology A. We show that as soon as this node shifts from technology B to A, your number of interface edges strictly reduces. So you can see before shifting, the number of AB type of edges involved here are capital N. These are your AB type of edges, and since there are N neighbors who have adopted A, the number of edges is N. Similarly, the number of BB type of edges which are outside this oval will be equal to M. We have already when we started with the lemma, we have already taken this assumption that your cascade capacity, it can so we have already assumed that our cascade capacity, it was greater than 1 by 2, and after that we show that your process will stop after a finite number of steps. So in this case, your value of Q, Yeah, so if the cascade capacity is 1 by 2, it means that the value of m should be less than n, because at least half of your neighbors should have adopted A in order for you adopting this technology A. So the value of m is less than n. Now let us see what happens after the shift. After the shift, the node yellow will come here, and all these and consider that all these interface edges, AB kind of edges, will convert to your AA kind of edges, and all the edges here which were BB kind of edges, they will convert to your interface edges, that is AB edges. So the number of AB type of new interface edges that you will be having now is m, and we have already seen that the value of m is less than n. So we can clearly see that the size of the interface reduced. So here we have proved that as soon as a node shifts from the technology B to A, the size of the interface strictly reduces, which shows that after some finite number of steps your process stops, and hence it is not a complete cascade. Next we try to see the compatibility and its role in cascades. So we have already discussed the theory of coexistence, where we have seen that two technologies simultaneously can exist in a network, and coexistence is not a rare phenomenon. Coexistence generally happens and it is very common. For example, A and B, they can be your two different languages which are coexisting along a national border. So we already know that there are a lot of languages spoken in South India, and all of them have a very well defined border. Similarly, your A and B, they can be two social networking sites that appeal respectively to students in colleges and to the students in high school. Now, currently, according to our model, if you are at the boundary or at the interface, it means that some of your friends have adopted technology A and some have adopted B. So till now you had to make a clear choice whether you should adopt A or B. It is like if you have some of your friends who speak Tamil and some speak Punjabi, you have to clearly explicitly state whether you are going to speak Tamil or Punjabi. But when people are actually faced with such situations, they become bilingual. You may start speaking both Tamil and Punjabi. So like as we previously discussed, if everyone in IIT Ropar uses Windows but everyone outside uses Apple, you may start using both. In that case, you get the payoff from both of the people who speak Tamil and who speak Punjabi. So let us try to see how do we model such a phenomenon. So here, instead of two technologies A and B, we have three, A, B and AB. So there are people who know A, there are people who know B, and there are people who know AB both. So if you are a person who knows only A, you will get a payoff by being with a person who knows A or who knows both A and B, but not with a person who knows only B. Similarly, if you are B, you will get a payoff of if you be with a person who knows B or A and B both. What if you are a person who knows both A and B? Obviously, you can only get a payoff of A from a person who knows A and a payoff of B from a person who knows B. Now, if a person who knows A and B comes in contact with another person who also knows A and B, in that case, you can always choose. You can see which out of A and B gives you both payoff, and you both can interact using that particular action. Okay. So before going further, now the thing is that if you know that you become bilingual, you will get multiple payoffs, both from people who speak Tamil and from people who speak Punjabi. So in this case, every person residing at the boundary can become bilingual, and that is a very perfect case. But there is a problem with this. Bilinguality also comes with a cost. If you want to adopt two technologies simultaneously, it comes at a cost. You need to buy some new software, or in the case of a language, you need to go to some classes, you need to spend some resources and efforts in order to learn both the languages. So we assume that if you want to use both the technologies A and B, you will incur a cost one time. We call this cost as C. Okay, so now let us consider this example and let us try to model it. So this figure shows you a network where the nodes R and S are A and rest of the nodes are B. Now let us see how will this cascade go around. So for modeling it, I have not mentioned the value of C here. C here is 1. That is, if you want to use both A and B, you have to incur a cost of 1. So let us try to look at how B is going to take a decision. How the node V is going to take a decision. So node V, if it adopts the technology A, it will only get a payoff of 2 from R and it will get a 0 payoff from X. If V adopts B, it will get a payoff of 3 from X and a payoff of 0 from R. It means that till now it is better for V to adopt B. What if we adopt both A and B by incurring a cost of 1? In that case, it will get a payoff of 2 from X and a payoff of 3 from R, total 5, and we subtract 1 for the cost that incur, so it will get an overall payoff of 4, which is better than both of the previous cases. So in this case, we will shift to AB. Similarly, you will also shift to AB, and if you see if this process continues, or many nodes are going to shift to both of the technologies AB. Now, I would like you to solve this example for some different values, where the value of A is 5 and the value of B is 3 and the value of C is still equal to 1. So if you try to model this phenomenon using these values, you will see a very interesting phenomena happening. You can see that after some time B becomes vestigial. There is no longer any point for a node to use it. Thus all the nodes, they abandon B completely over time. So in the long run only A persists.